this module, we will talk about water resources engineering. All of us are aware of the importance of water and the scarcity of water resources. So we must use optimally whatever resources are available to us. And before doing that, we must know how or in what forms water is available, its spatial and temporal distribution, and for that, the first thing which we will discuss is the hydrologic cycle. As you can see in this figure, the hydrologic cycle or the water cycle consists of various forms and movement of water. Let's start with this ocean. In the ocean, due to the solar radiation, there is a lot of evaporation of water. When it goes up, it condenses, and then there is some precipitation in the form of either rain or snow. We will discuss these forms little later. When the rain falls, there might be some evaporation directly from the rain, and the rest of it, when it falls on the surface, either goes into the ground as infiltration, or it runs off in the rivers or deposits in the lakes. Now, these rivers then run to the ocean, and this cycle continues. There are a lot of components of this cycle which we are interested in. For example, if we are working in the field of irrigation engineering, we would like to know how much water is going into the ground and from where the plants can take their water. But if we are, for example, for this module, we are concerned about the water resources, then we should know how much water is going into the rivers so that we can control the floods, or we can avoid a lack of water for irrigation in other areas. So let's look at some components of this. Precipitation, we will start with discussion of precipitation, its various forms. In India, we would typically worry about rain, snow, and hail. All of us know what is rain. Snow, of course, we have seen. In India, it's not a lot, but in some of the Western countries in colder climates, snow is also an important part of precipitation. Hail, drizzle, sleet, and glaze, these are all different parts of precipitation. In your chemistry classes, you must have seen precipitation of solids in liquid. So in similar form, you can think of rain as precipitation of liquid in gas. So in the atmosphere, there is a lot of water vapor. When it cools down, the condensation causes that water vapor to drop in the form of rain or snow or hail, depending on the temperature at that time. Various forms have sub-classifications also. For example, rain can be classified as light, medium, or heavy, depending on how much rain is falling in, let's say, 1 hour. When we study the mechanisms of rain, it can be caused by various different kinds of mechanisms. The important thing is that there is a mass of water vapor which should cool down so that the water condenses and then falls down. So for cooling, we have a lot of different mechanisms. For example, the frontal mechanism, where a front, which is a surface or a surface of contact between two different air masses of different temperature, when a warm front or warm air, for example, if this is the ground surface and there is warm air blowing from this side and it encounters a cold front here, then this warm air tends to rise above the cold air because of its smaller density, and therefore as it goes up, due to adiabatic rate of cooling, this water vapor will condense and will fall down as rain. So this is called frontal precipitation. In the next form, which is the convective precipitation, we have surface of the earth which may be warmer, and therefore the air which is in contact with the surface because of its high temperature and low density tends to rise and sets up a convective current. Now when this air rises, again when it goes up it cools down, and therefore there will be some precipitation in the form of rain. The third mechanism is called orographic precipitation, and in this form, if we have, let's say, a mountain and air coming in, it will rise because of the rise in the ground elevation, and then as it rises up, again the temperature decreases and there will be some precipitation which is known as the orographic precipitation. And then finally cyclonic precipitation, which occurs especially in coastal areas where from the sea cyclones, which are winds of very high magnitude and rotating about a center, they carry a lot of moisture from the sea, and then when they come on land they will cause precipitation. Now with precipitation, it's important to know how much precipitation is occurring at a certain time, and therefore the next topic which we discuss is the measurement of precipitation. There are basically two different types of instruments which are known as rain gauges. One is a simple non-recording and the other is a recording. Non-recording means that it will not record with time a continuous variation of rainfall. We will go manually and maybe once a day see the instrument and see how much rain has collected. And in recording type gauges, we have a continuous record of rainfall. As it is falling, it is being recorded. In the non-recording rain gauge, this figure shows a typical non-recording rain gauge in which on the top we have a funnel to carry the rainwater falling on it. This funnel then carries water into a graduated cylinder on which we can see the markings which tells how much rain has fallen in that period. Typically in India, around 8 or 8:30 a.m. a person goes and looks at this rain gauge and finds out how much rainfall has occurred in the previous day. So a fixed time every day somebody goes and watches the amount of rainfall. In the recording gauges, we have a continuous record. There are three different types of rain gauges commonly used here. The most common one is known as a tipping bucket. In the tipping bucket rain gauge, which is shown here, again we have a funnel which collects rainfall, and there is a arrangement here which is known as a tipping bucket, which has two compartments as shown here. One of the compartments is below the funnel, so it collects all the water, and when a fixed amount of water has entered into this bucket, it tips over. So then it rotates and the other compartment comes below the funnel. So this will go here and the other compartment will come below the funnel, and then it will start collecting. And when it tips, there is a magnet here which will send a signal to some recording device, and we will know how much time it took to fill one side of the bucket, and we know how much rainfall has been collected in that time. So that way it records these tips which tell us what is the intensity of rainfall. The data which we obtain from these non-recording and recording gauges can be expressed or displayed in a form of a hyetograph or a mass curve. Now a hyetograph is a plot of time versus intensity. Intensity of rainfall is typically expressed in terms of uh, millimeter per hour, sometimes centimeters per hour. And if we have a non-recording rain gauge, then this what data we'll have can be expressed as daily values of intensity. For example, in the first day, if we collect 2 millimeters of rain, we can express the intensity, and it would be better in that case to change it to millimeter per day. So we have 2 millimeter in the first day, then suppose in the second day we have 3, so it will look like this. And since we don't know when in the day this rainfall occurred, because we are collecting data only every 24 hours, we cannot show the variation within that one day. So this typically would look like this, and so on. So this is known as a hyetograph, how the rainfall intensity varies with time. The second type of curve which we use to show the rainfall intensity variation is a mass curve. And a mass curve, again with time, shows the accumulated depth. So the intensity shows how intense is the rainfall, how many centimeters or millimeters per hour, and a mass curve shows how much depth has accumulated from the starting. So again, if we say that this is time and day, this accumulated depth may be in millimeters or centimeters. So in the first day, if we have, let's say, 2 millimeter of rain, it would be 2. Then in the second day, suppose we have another 3, then this would be 5. So this curve is continuously increasing because it tells you the accumulated mass or depth of rainfall. For recording gauges, we typically get a curve which directly gives us the accumulated depth. In the recording gauge, the tipping bucket we have seen, but there's another one which is not so common because it's more expensive, and which is known as a weighing type. In the weighing bucket, as the rain falls on the bucket or on the rain gauge, it gets collected and a signal is sent immediately to record how the weight is increasing with time. So what we get is a directly mass curve of rain which would look like this. Again, this is depth, maybe millimeters or centimeters, time maybe in hours or day. So this shows the accumulation of rain in the rain gauge over time. And if you look at this curve, it tells you that there is no rain from this point to this point. There is some rainfall. The slope of this curve will show you the intensity of rainfall. So wherever the slope is largest, for example here or here, the intensity of rainfall is very high, and where it is flat, there is almost no rainfall or very low intensity rainfall. So the mass curve slope will give us the hyetograph. Okay. Now to collect the data, we need to put these rain gauges in the field, and therefore it becomes important to know what should be our network. For example, if we want to find out the rainfall over a certain area, how many rain gauges should be put, where should they be located? For example, one option would be to locate the gauges here, or you may add more gauges here. So there are some guidelines which tell you in how much area how many gauges should be used. For example, in India, the guidelines are for 1,000 kilometer square area, if we have plain area, 2 rain gauges are sufficient. If you have moderate elevation, for example 1,000 meters elevation, then you may need 3 to 4 rain gauges in 1,000 kilometer square area, because the variation of spatial variation of rain is likely to be more than in the plains. And for hilly areas, typically we need to use 8 rain gauges over 1,000 kilometer square area. So these guidelines should be followed whenever we are designing a rain gauge network. And another guideline is that 10% of the rain gauges should be of recording type. So if we have let's say 15 gauges in this area, 1 or 2 should be recording, and based on the record of those 1 or 2, we can estimate the temporal variation of rainfall on the other stations also. That's why these 10% recording gauges are to be used. Once we collect the data from these gauges, we have to analyze the data. So the next thing we will discuss is the data analysis. In the data analysis part, let's start with, suppose we have a network of rain gauges like this, and we have collected the data over, let's say, a period of a year. Now some of the data may be missing. For example, there may be a rain gauge here where we have data for every day, but one day the person who was supposed to collect the data could not go there, and therefore we have a missing data. So how to estimate or how to take care of the missing data, that is the first thing we will see. If we have collected data for a number of days but we have missed one day, how to estimate that missing value. The easiest thing, of course, is to see that if we have missed values at one station but we have the values available at all the other stations, we can take some kind of mean of all the other values and say that that will be the value at this point. So if we have, let's say, m other stations, then we can say that the missing value at x could be the mean of all the other values of precipitation on that day, and we estimate our missing value of Px using this. But there is a problem with this method when there is a wide variation of rain over the area. So for example, this gauge may be recording a higher rainfall than this gauge in general. So that's why we have to look at normal precipitation at various gauges. When we say normal precipitation, typically we say normal is taken as a 30-year average. So if we are looking at, let's say, May 18th, then we would consider what is the rainfall at those stations on May 18 over the past 30 years. And the average of those values would be called the normal precipitation for that rain gauge for that day. So if we are missing the precipitation at this station on May 18th, we can estimate it based on the precipitation on that day for all the gauges and their normal values. So the formula which we use in this case takes care of the variation in the normal rainfall at other stations also. So it's similar formula, but now instead of estimating the rainfall, we estimate the ratio of the rainfall with the normal rainfall, and that way we can estimate what is the missing value Px. The next important thing to look for is whether the data is consistent or there is some inconsistency in data. For this purpose, we use what is known as a double mass curve. The assumption is that if the data is consistent, it should follow the same trend over a number of years compared with the other stations in that area. So we plot a double mass curve which is accumulated precipitation at let's say 5 or 10 nearby stations versus the precipitation at the station where we want to find out whether the data is consistent or not. And if the data is consistent, typically it would follow a straight line with minor variations. But if there is some change in the characteristics of the catchment or the gauge has been shifted, there is some inconsistency, then we would see that the data does not follow a single straight line and it may deviate from that position. So if we plot the most recent data here, and then if there is a break somewhere, let's say we are starting from 2006, and then we find that in 1980 there was a break in the curve. So it will tell us that the data is not consistent and there is some problem. Either before 1980 the gauge was at a different location and then it was shifted, or there was some change in the pattern, precipitation pattern, because of some natural factors. For example, there may be a lot of vegetation which was removed. So there could be a number of factors causing this behavior, but any inconsistency in data can be obtained by the double mass curve analysis by plotting accumulated precipitation at one station versus accumulated precipitation at a few nearby stations. Okay. Now once we estimate the data and check that this is consistent, we go for areal averaging. So if we have certain area and we want to find out rainfall over this area, the values which we have for precipitation is only at these rain gauges, and these are called point values. Out of these point values, now we want to estimate what would be the average rainfall over this whole area. So let's call this area A. So the problem is, given the point rainfall values at the rain gauges, how to estimate the average rainfall over the entire area. There are a number of techniques again to do this. The simplest one is known as the arithmetic mean. And as it is clear, arithmetic mean means we just take the mean of precipitation values at all the stations. So if we have, let's say, these 8 stations, we will say arithmetic mean, our mean precipitation over the area would be sigma of Pi over 8. So I equal to 1 to 8. So it will take the mean of all the precipitation over the entire area. The drawback with this method, although it's very simple, is that we don't give any weight to the location of the gauges in that area. So if we have an area where let's say 4 gauges are here and 1 gauge is here, we take the mean without considering that these 4 are very near, so they don't represent as much area, or this one is here, so how much area does it represent? It's not accounted for in the arithmetic mean method. So a modification or an improvement over this was proposed by Thiessen, and this is known as the Thiessen polygon method. In which the relative position of the various gauges is also considered. So if we have rain gauges in an area like this, we draw perpendicular bisectors of the lines joining the rain gauges, and then we assign, suppose this is rain gauge 1, 2 and 3, we say that area A1 is effective area for the rain gauge 1. Similarly, area 2 and area 3. And then when we compute the average precipitation, we give the weight to individual rain gauges. So P1 A1 by A plus P2 A2 by A So this tells us that a certain weight A1 by A, depending on what area is covered by rain gauge 1, is assigned to the precipitation of each rain gauge. So this takes care of some of the drawbacks of the arithmetic mean method, in that it accounts for the position of the gauges. But it does not account for variation in topography. For example, there may be mountainous area here and there may be plain area here. So if there is a sharp change in elevation, the Thiessen polygon method will not be able to account for it, and therefore we have another method which is called the isohyatal method, which accounts for the variation of topography also by looking at individual precipitation values and drawing isoheights. Isoheights are nothing but lines of equal precipitation. So if we have the precipitation values at all these stations, we could look at those values, and using those values we could draw isoheightal lines. For example, this rain gauge, this may be 8 millimeters, 10, 12, depending on the values of these rain gauges. So all these rain gauges will have values between 8 and 10. This will have less than 8, this between 10 and 12. So we will draw these isoheights, and then we will assume that the area between two isoheights has a rainfall which is equal to the mean of the values of these two isoheights. So this area will have a rainfall of 9 millimeter. And by summing up the area and the rainfall over the respective areas, we can get the average rainfall over the area in terms of P bar. And suppose P1 and P2 are the P1 and P2 are the surrounding isoheightal values, and A is the area between them. Then we simply sum up the average precipitation into the area for all the isoheights in the area. Now, once we get the areal average, we can know what is the depth of rainfall over a certain area, and then we can prepare what are known as depth, area, duration curves. Now, these curves look like this. This is the area which may be in kilometers square, and average depth of rainfall which may be in millimeters or centimeters, and this will show the duration of rainfall which may be 6 hours, 12 hours and so on. So this is the duration. Now if you look at a typical storm, the center of the storm, the intensity will be the largest, and therefore the depth will be very high. As you increase the area, that means you are moving away from the storm center, the intensity decreases, and therefore the depth also decreases over the area. Now if the storm is of larger duration, the depth will increase. So these kind of curves will tell us how much average depth of rainfall to expect over a certain area if the rainfall occurs for a certain time, which is 6 hours or 12 hours or any given time. There is sometimes an empirical equation also given for variation of rainfall average depth with area as minus k e to the power n exponential, where P0 is the point rainfall value which we obtain from the rain gauge. But since the rain gauge will not always be at the center of the storm, typically we say that this rain gauge value represents the rainfall over a 25 kilometer square area. So this kind of equation tells us for any given duration the average depth decreases with area. These values of k and n will depend on the catchment area, and some typical values are given in various textbooks about different areas. The other aspect which is important is to have some kind of frequency analysis or risk analysis to see what are the chances of rainfall occurring in the next 10 years or next 100 years or so. So the frequency analysis is also very important from this point of view. So frequency analysis is nothing but deciding how frequent a rainfall would be, and typically what we do is present an intensity, duration, frequency curve in which we say how frequent will be rainfalls of certain intensity and a certain duration. So the curve would look like this. This is the intensity of rainfall, which may be millimeter per hour, duration typically in hours, and this denotes the frequency or the return period. Which may be a rainfall of once in 100 years or once in 20 years or once in 50 years. The frequency of course would be reverse of the time period. So we can write the time period as 1 over the probability of occurrence of a rainfall, and when we discuss the intensity, duration, frequency curve, they will help us in knowing or designing a project or some structure against a given probability of occurrence. So if we want to design something which is to be very safe, we may go in for 100-year precipitation, and based on that 100-year precipitation we can find out what will be the depth of precipitation, and those curves we can prepare in terms of duration, depth of rainfall, and the time period. So what this curve indicates is that for a given duration of rainfall, what will be the depth for a given time period. One should be aware of the fact that time period of 100 years does not mean that this rainfall will occur every 100 years. In general, if we take a very long period of records, for example, 400 years, 500 years, this event is likely to occur 4 or 5 times. It's not that it will occur only once in any given 100-year period. And related to this, there is a concept of probable maximum precipitation which can occur over a given area, and this probable maximum precipitation is used in very extreme cases where we have to design something which is very critical. For example, a large dam, the failure of which will be catastrophic. So in that case, we can find out what is the PMP, the probable maximum precipitation, which is typically written as some factor multiplied by the standard deviation in plus the mean rainfall, and generally the value of k is taken as about 15. So the mean rainfall plus 15 times the standard deviation is now normally taken as the probable maximum precipitation for that area, and this is used in critical designs to estimate what will be the maximum flood which can occur in a given catchment. So in this lecture, we have seen at various aspects of precipitation, but we must realize that as water resources engineer, it's not the precipitation which is of importance to us. It is really the runoff, or how much water is going into the rivers, which is more important to us. Although if you are an agriculture engineer, the water which is going underground may be more important to you, but most of the water resources engineering projects deal with construction of dams, canals and other things from the rivers, and therefore the volume of water going into the river is more important, although it depends on precipitation, but we are more concerned about the runoff. So in today's lecture, we have looked at the precipitation. Out of this precipitation, part of it will go underground, which is called infiltration. Part of it will evaporate from the surface. Part of it will be lost as transpiration from the plants. So we combine them and we call that evapotranspiration. So evapotranspiration and infiltration, these are the two abstractions from the precipitation, and the most of the rest goes to the streams or over the surface as surface runoff. Part of it goes inside the ground and again goes to the streams and ocean as underground runoff, or what we call base flow. So after today's lecture, in which we studied precipitation, next we will look at what are the various abstractions with infiltration, evapotranspiration, and there is some storage on the surface to see how much water is taken out of the precipitation, and that will help us in finding out how much of the water is going into the rivers and lakes.